Section 5.3 covers the fundamental theorem of calculus, part 1 and part 2. There's 2 parts to the fundamental theorem of calculus. We call them FTC 1 and FTC 2. They may seem kind of like duh theorems to you, but if you think back to the first time when Newton and Leibniz really realized, and people before Newton even realized, that the antiderivative and the derivative, or the integral and the derivative, were inverse processes, it was a big deal. So Newton and Leibniz started to give out that information and explore it a little further, but the fundamental theorem of calculus is that theorem that states that integration and differentiation are inverse processes. So it's kind of a big deal, but you'll see what we do with these in AP Calculus. So the first part of the fundamental theorem of calculus says that if f is continuous on a, b, the closed interval, then the function g, if it's defined by g of x, equals the integral from a to x of f of t dt. Notice that the independent variable in the f function is t, and that the independent variable in the g function is x. X is between a and b, so x is in the area where the function is continuous. If g is continuous and differentiable on the open interval a to b, then, well, it says that g is continuous because f is continuous, and then g prime of x equals f of x. Now, what that means, let's think about it in real words. What this really means is that g of x equals the area under the f of t curve from a to x. So if we can look at it in this example down here, this means here that g of x is the area under the f of t curve over here from 0 to whatever the x value is that you're in g. So we can use this to evaluate values of g by interpreting them in terms of areas. So let's look at g of 0. This would mean the integral from 0 to 0 of f of t dt. Well, if we're looking, that would mean the area under the curve of f of t from 0 to 0. Well, that's no area. That's easy enough. 0. Let's do a harder one, though. Let's find g of, do an easy hard one, g of 1. So let's look at the area under the curve from 0 to 1 of f of t dt. What is that area? Well, it looks to me like a triangle. The area of this triangle is 1. 1/2 times 1 times 2 is 1. You can find other values of g, g of 3, g of 4, just by calculating the area underneath the curve. If you want to look in your book, example 1 continues this problem on in this section. So if you're unclear, their pictures have grid lines, so it's a little bit easier to count the area under the curve. You could look real quick, though, if you wanted to just make sure you understood. You could look and see what g of 2 would be, the area under the curve from 0 to 2 of that f of t curve. And if you look at that closely, it'd just be the triangle plus a rectangle. The area of the triangle is 1. The area of the rectangle is 1 times 2, or 2. So the area under the curve there would be 3. G of 2 then equals 3. So the first part of the fundamental theorem of calculus, that's really all it says. Let's look at the next little piece of that first part of the fundamental theorem, though. It says that if g of x equals the integral from 0 to x of some f of t dt, in this case our f of t is square root of 1 plus t squared dt. If we want to find g prime of x, all g prime of x is going to be, according to the fundamental theorem of calculus, this slide before, all g prime of x is going to be is f of x. My f function here is the square root of 1 plus t squared. So my g prime of x is going to be the square root of 1 plus x squared. That's f of x. I put x in for all the t's because this originally was a function of some variable t. Well, f of x would just look like an x in the place of the t's. It really is that easy. One more example that's a little more difficult when we get stuck with something that's not just a plain x in the upper limit of integration of your f, or in your g of x. This is just like saying g of x equals, got it down here, g of x equals the integral from 1 to x to the 4th of secant t dt. But we're taking a derivative of it, and you're going to see we're going to use a little bit of a version of the chain rule. Don't be scared about it. It's just a little bit of chain rule. So, in conjunction with the FTC1, we're going to have to use chain rule. So the derivative of this function is going to look just like plugging the x to the 4th in, but then we need to make sure to take the derivative of the x to the 4th as well. So g prime of x, or this derivative, equals times the derivative of x to the 4th. So basically, that's what you do. If you want the full explanation of why you do that, you're going to need to look at example 4 on page 390 in your book. You can plug in a u for this x to the 4th power and use the chain rule that way. But since we've never used the chain rule with the u for the function, just know that when you have an upper limit of integration that's not just a plain old x, you're going to use the chain rule. Now, does it matter what your lower limit of integration is on these? Not really. So just worry about the upper limit where the x is. So 4x cubed secant x to the 4th is a prettier way to say that. The fundamental theorem of calculus part 2, FTC 2, is basically tells us that it relates the antiderivative to the integral, but it tells us the way to find a definite integral, and we spoke about this in class already, so in section 5.2 a little bit. The proof of this fundamental theorem of calculus 2 is in our book on page 391. If you're into proofs, you want to check it out. It's a pretty easy one to read. But what it says is if f is continuous on the closed interval a to b, then the integral from a to b of f of x dx equals the antiderivative of the function f evaluated at b minus the antiderivative of the function f evaluated at a, where f is the antiderivative of the little f, such that f prime is big F prime is little f, just like we talked about before with antidifferentiation. So it's super duper easy to use. All we've got to do is say, take the antiderivative of this function inside, that's our f of x. Well, the antiderivative of e to the x is just e to the x, but I'm going to evaluate it from 1 to 3. So since I'm evaluating it with numbers, I really don't need a plus c. So e to the x evaluated at 3 is e cubed minus e to the x evaluated at 1 is e to the first. So the answer is e cubed minus e. Remember, e is a constant, so that's really a number, but we're just going to leave it because it's more exact, since e is a constant that would go on and on and on forever, and we'd have to round, and that would make it less exact. One thing to remember when you're integrating is that you're finding the area under a curve. So let's look at some more examples that you can practice on. If you're going to practice these examples, pause the video now, and then come back, and the answers will be on it. Here are your practice answers. What I want to draw to your attention is number 1 is pretty straightforward, but in number 2 I wanted to draw to your attention that you do need to remember to use your rules for natural logarithms. And if you've got logs with the same base and they are subtracted from each other, then that's the natural log in this case of a difference. So that would be the natural log of 2. Pay attention. Remember, log rules are not going away. In number 3, again, that's pretty self-explanatory. The antiderivative cosine is sine, and the sine of 0 is 0. So you end up with sine b. Whatever b is, you just plug that into the sine. In number 4, again, that one's pretty straightforward. I'm not worried about that one. Number 5 does something a little bit differently. Remembering, and if you did remember, you should pat yourself on the back, that you use your algebra skills to make it look the way you want it to look before you anti-differentiate a problem. Don't give up just because it doesn't look right. Use algebra to manipulate it to make it look how you want. We'll work more problems like this in class tomorrow.